Good morning, everyone. It's a privilege to be invited to give a talk, or at least a sense of where the field is in terms of uranium-lead dating. This work that I'll be talking about, I mean, the conceptual issues are obviously standard stuff, but as far as the data that I'll be sharing is the product of work that's been done in my lab, or has been done with my lab, especially Oana Dmitru, she's now at Columbia, the postdoc, Victor Polik here at New Mexico, and Dave Decker also did his PhD with us. And so what I want to sort of give you is a sense of the systematics, and then the sort of detail on how you implement that, and then share with you some results. And then hopefully I'll leave enough time so we can have a productive question and answer session. Give me a second here. In geochronology, like any other field of science, opportunities are always coupled to technical advancement and then also conceptual framework. Previously, I'm sure you've heard about uranium series work. We do a lot of that stuff too. It was known, for example, as far back as in the very early 1900s, these isotopes of uranium could be used for chronometry. Their application was limited, primarily not because of conceptual issues, but because of technical development. From J.B. Thomson's early mass spectrometer to our modern mass specs, basically, this has been driven by technical, to give you an idea. When I was young like you, I did a PhD work that included zircon geochronology. It required processing anywhere from 20 to 50 kilograms of sample to get 30 milligrams of zircon to get a decent date. Now we can do the same precision work with 20 to 50 milligrams of carbonate. And so it's always, I think, as you guys are getting started in your career, it's always good to take advantage of developing new techniques and always be there. You know, I got started on this whole thing, as I said, it was early uranium lead. And then I moved on to Minnesota to work with Larry on uranium series. And so I'm always opportunistic in terms of taking advantage. The uranium thorium system is a really wonderful, rich space for chronology. You have two isotopes of uranium that decay to two isotopes of lead, one isotope of thorium that also decays to one isotope of lead. The lead-204 is the only non-radiogenic. Given the different half-lives and abundances, you can trace basically multiple chronologies from the beginning of the solar system to what I call the recent past. I'm sure you have covered already uranium series. Just want to point out just a critical couple of points. First is the decay of uranium-238 to 234 through two steps in here to thorium-230. That has implication for uranium-lead dating, especially when you're dealing with young samples. The other thing is the decay of 235 uranium to protactinium-231. That also has implications. The 232, 208 system is relevant for igneous and other clastic systems because thorium is not soluble in water, so I won't focus on the 232-208 system today. So basically, given the richness of the space, you can have 5 chronometers. First, you can use the 208, 206, and 235, 207 system as standard isochron system like any other radiogenic isotope system. But because of the coupled decay of the 2 uranium isotope to 2 lead isotopes, also it can create a unique chronometer space, which we call the Concordia diagram, in which each point basically falls on a specific point on a line, and you don't need an isochron if you're able to get a concordant sample. Obviously, because of the coupled decay, you can also have purely lead-lead edges. The lead-lead edges are not quite useful for recent work in carbonate because the initial ratio variability affects it, and I'll show you why it may not be all that useful. And then, as I said previously, the thorium-232 lead to O8 system is not useful for carbonates because thorium is not soluble in water. You know, part of the chronometer is the ideal chronometer is a system in which the parent is accessible and the daughter is not very mobile, and therefore in a system in which let's say in the cave environment, in an oxidizing fluid based system, uranium as a +6 is mobile. Lead, not so much, unless you have extremely low pH environment, which is not the case. Typically in caves, you have very high pH. And then thorium, because it's not soluble, it's not possible to do the 208, 232 to 08 system. There is a nice convergence in my lab. We do both systems, both uranium series and uranium lead, because the set of problems we're working on, especially when it comes to climate, sea level, surface process, neotectonics, cover the full range of what I call the recent past to very ancient times. The uranium series system is ideal for more recent stuff. So this is kind of schematic illustration I put together to give you a sense of age uncertainties. So if you can just say the limits are infinity in here, within the first 100 years, neither uranium lead or is not going to work very well. And this is just simply, the uncertainty is simply unbound. For uranium series, under ideal conditions, for example, when you have high uranium concentration aragonite, you can actually get very decent uncertainties, even in things that are, you know, a couple of 100 years old. As you move forward, basically, the uranium series uncertainties diminish because of two things. First, you are generating thorium-230, but more importantly, the unsupported 230 essentially decays away. So when you get to the scales of 200, 300,000 years, we can actually date petagenic carbonates quite very easily. And then the subject of my talk here, which is the uranium lead, you get to a point then about 700,000 years or older, where actually, first of all, you lose the capacity to get any information from your uranium series after that, or 600,000. And then after that, basically the errors on the uranium lead diminish significantly. In fact, the older, the better, as long as you can maintain the system as a closed system. Basically, let me just give you the nitty-gritty, not in too much detail, because some of these procedures will depend on which lab you go to and what columns they use. So just kind of give you a quick rundown of what we do here. Typically, we start out with 20 to 50 milligrams of carbonate. Ideally, it'd be nice to get aragonite or high uranium calcite. If not, we manage to do carbonates that have a few hundred parts per billion uranium concentrations. And then we dissolve the sample. Sample prep, as I said here, the less the better. So typically what we like to do is break chips and not process them any further. Basically, we take individual chips, do cleaning, and then dissolve the samples. And then basically, after the sample is dissolved, we add uranium, lead, and thorium spikes. In the lab, we always do uranium series and uranium lead at the same time for the full spectrum, because we'll need the information from uranium series, for example, to correct for 234. So we have a double spike of 233, 236, which is nice. That allows us to measure abundances, but also fractionation. We have lead 205 spike. Other labs use 205, 202 lead mixed spikes, which allows them to do fractionation correction. We don't do that. We prefer just simply to do the 205 lead spikes. And then we use lead standards such as NBS 981 to establish fractionation with every sample. And then we have thorium 229 spike for doing the 230, 229 measurements. The mass spectrometry for lead isotopes, typically a lot of people like to use thermal ionization because you have less fractionation than inductively coupled plasma mass spectrometry. We have a TIMS, but we ported most of our work on the ICP, our Neptune. It's just much more convenient. And so we do the measurements in the plasma. The one good thing about the ICP is that we can do sample measurements and then measure standards in between to establish fractionation corrections for things like our thorium measurements and lead measurements. So this is kind of the simple schematics of how mass spectrometry works for those of you who are not isotope geochemists. So basically, the idea of mass spectrometry is you're trying to ionize, first of all, you do chemistry. The chemistry part is separating the element of interest. In this case, over here, the solution, you use ion chromatography to separate the elements of interest, because in mass spectrometry, the same masses, regardless of the elements, cannot be separated out, at least with the kind of resolution that we have. So you have to separate the element of interest during mass spectrometry. And this is our stepwise sort of elution system to separate out uranium, lead, and thorium. So once you have your element of interest, then you ionize it in order to generate either positive ions or negative ions. In our case, we use positive ions with the Neptune. And the way you ionize is traditionally you could use thermal ionization mass spectrometry. You're just using like a tungsten wired like in a light bulb. You hit the thing to about 2000 degrees, or depending on what element you're analyzing, and then basically have these charged ions. With ICP, you're using induction basically to generate very hot temperature to create a plasma. So the ionization efficiency is huge, basically. Unfortunately, it's a little more chaotic than thermal ionization. Once you have charged ions, then you can accelerate them by creating an electric field. So essentially, you have this gradient in here that goes, say, from 10 kVA to 0. So the charged ions will go racing down the flight tube. And once they get to the flight tube, they go through a magnet. And in the magnet basically is able to deflect charged ions. And then at the end of the magnet, something I call the law of the street takes over, which is the little guys get pushed a lot more than the big guys. And then at the end, you have your little Pokemon collectors. I'll talk a little bit about the collectors. And then you can just, using whatever computer you have, you can measure the different ratios relative to each other. One of the real advances besides ionization has been in the sort of collection technology, especially when it comes to Faraday cups. The Faraday cups are just simply electronic cages that are coated in carbon, let's say. And essentially, when you put charged ions, they neutralize them. You create a potential in here. By putting a resistor across the potential, you can get voltages. On these resistors, typically are dealing with something like 10⁻12 amp scale signal, very low signal. And then when you put, let's say, 10 to the 12 ohm resistor, you get 1 volt. And one of the things that have really improved our situations, Faraday cups are really good, reliable measurement devices. Until recently, it was very difficult to get resistors that are very quiet. There is a Johnson noise thing that I don't want to get too far into. But right now, though, we have resistors that are very quiet in the range of 10 to the 12 ohm resistors, 13 ohm resistors that actually we are able to measure a lot of the stuff that used to be measured in electron multipliers now with Faraday cups. So that has really improved things. Of course, with our secondary ion multipliers, we can do single ion counting. And again, this has been truly amazing. And this is the difference between why I had to do 30 milligrams of zircon when I was young, and now we can do 10 milligrams of carbonate with the same system, or less for that matter. Obviously, the governing thing is counting statistics. So you can measure a number of ions, and basically what you want to get is the number of ions, because your ultimate precision is limited by 1 the square root of n. So when you take a decision, you have to balance between sample size. Obviously, in a stalagmite or any other carbonate, there is also an age constraint about how much sample you can take from any given area, because you don't want to, the most precise number, but absolutely meaningless number would be to crush a whole stalagmite, get a huge amount of thorium, uranium, and lead, and get very, very precise number, but it doesn't say much because you're sampling over a very large area. So the trick is to always have a compromise between sample size and also precision. Now, for the work that I'm showing you right now, we were not trying, or people like Juana were not trying to achieve the most precise numbers, but rather to get very good chronometers within the sort of limits of the samples or the nature of the sample. Give me a second, I have to clean my board. So, as I said, one of the issues that you have to deal with uranium lead for young samples is that typically waters are not in secular equilibrium when it comes to uranium-234. For example, in continental waters, such as waters that are coming from a, say, sedimentary aquifer, you can have very large enrichments in uranium-234. Typically, uranium-234, I'm sorry that I have to cover some your series stuff already covered, but just cover my base. The enrichment is measured as a delta number relative to the secular equilibrium number. That's always known. It's just simply the ratio of the half-lives of the 234 to 238. And so let's say seawater, for example, has a delta enrichment of about plus 150. Many of our samples can have enrichments in the range of 3,000. Or in some cases, when you are in a tropical region where there has been a lot of leaching, you can also have the negative delta 234. So for young uranium lead samples, you really do have to do the correction for 234. The challenge, of course, is once you get about beyond the 8 half-lives of uranium-234, say beyond 2 million years, that enrichment information is completely lost. So you have to somehow reconstruct it. So the strategies that one can use is, for a lot of our work, for example, the work that Juana has done in Mallorca, our samples range from recent to very ancient, and we seem to find reasonably consistent delta 234s. So if you have a time frame that covers when 234 can be measured, and then also the samples using uranium series, you can get the initial 234 from the uranium series and then apply that correction directly. In other cases, you have to use a different strategy. One strategy is that, so you have 234 eventually decaying to 206 from 238 rather. And then for 235, you have 231 protactinium decaying to lead-207. So what you can do in the case where you don't have information on the initial 234, you can estimate the amount of 234 enrichment by looking at the 207, 235 age, and then co-adjusting the 234 for the two edges to get close enough. The justification for that is, oh, sorry, protactinium is PA, sorry, not PB, is that protactinium, unlike uranium, is a high field strength element, just like thorium, and therefore is not, we don't think it's enriched all that much. So the 2035, 207 system probably is reasonably robust without having to worry about 231 correction. Someone could correct me if they have another experience. And then basically by having this adjusted and getting the 234 number, then you can calculate a more precise age. And then for samples that are very, very old, well, the 234 initial enrichment, unless it was very extreme, should be significantly small compared to your other errors. and therefore you live with that basically. For most of the work we do, because we are interested in the recent past, that's something we look at very, very carefully to make sure that our corrections are robust. So even though I'm not going to go into the detail about how you do the corrections, we have to correct for 234, fractionation, spike corrections, and all that stuff. So let me start out first with the isochron systems. As I said, disregarding the thorium-232 lead-208 system, you have the 238-204 system. For those of you who haven't taken radiogenic isotopes or you have never had, essentially this is the standard decay equation. The amount of, let's take lead-206 you have is equal to what you started with at the beginning of the system plus the production term. The production term is basically the amount of uranium-238, right? Times the exponential of the decay constant of 238 times the time in which the system was separated, i.e. the age minus 1. You can do the same equation for 206, 204 and get two independent sort of isochrons for the system. This is an example from one of Anna's samples, Majorca AR03. This is a lead to uranium-238, lead-206 isochron. It has an age of 320 plus or minus 0.18. We always report our errors to sigma errors. And the 235-207 system also gives a concordant age, even though about 5 times more errors, because the amount of 235 and 238, basically for every 138 atoms of 238, you only have one atom of 235, and therefore the amount of lead-206 is going to be smaller, and therefore your analytical errors are going to be larger, even though they may be concordant. Before I move forward, are there any questions specific to some of these things before I go too far? So if you notice, the age equation basically is what you measure in the lab, right? You don't necessarily know the initial. You can measure this in the lab. And this is an equation of the line, right? Y is equal to B minus AX, or XA, A being the slope in which you get the age. The initial ratio obviously is a projection when X in here is equal to 0. So for a standard isochron, you can essentially get the initial lead-206 to 04 by doing this isochron work. Okay, so for those of you who do silicate type work, you can construct the same isochron for 232 thorium-208, but because of the long half-life of 232 stuff, not terribly useful even in other systems. You can also get, because of the coupled decay, what are called lead-lead edges. I used sort of my 10. I didn't want to go through PowerPoint and get all these ratios. All I'm trying to show is basically you can have basically the lead isotope composition, the radiogenic isotope, divided by the 206 divided by 207 is equal to 137.88, and then basically you have time. So you don't need to know the uranium concentration to get lead-lead edges. That's a good thing. So, for example, for much older samples, you can do laser ablation lead isotope data without ever having to worry about it. For carbonates, it doesn't work all that well, for at least young ones. This is an example of the previous isochrons that I showed you for that sample. This is the lead-lead system. It's very meaningless. The errors are very large, and therefore you don't get really meaningful edges. We've done lead ages for things that are much, much older, like some of Dave Decker's work that was, over 60 million years. Then you can get sort of the lead age. Otherwise, for more recent carbonate work, this is not terribly useful. So then we get into this wonderful space, again, because of this coupled system of Concordia diagrams. This is what's called a traditional Weatherall Concordia diagram. For this system, you have to know the initial in order to get the radiogenic to 06, radiogenic to 07, then divided. And basically, I've just shown you here how you reduce the equations into this. And therefore, because of this coupled system, basically, every point on that blue line is an edge. You don't need an isochron. You can get an edge. If, in fact, your sample has been disturbed, you can get still not lost. You can do a secondary isochron or a Discordia chord in which you get an upper intercept and lower intercept. I'll talk the inverse Concordia diagram, which is more appropriate in this case. But for those of you just for general interest, in this case, the upper intercept could be a crystallization edge, and the lower intercept can be an edge of metamorphism or change. Or in some cases, the lower intercept edge could be the crystallization edge, and the upper intercept could be the edge of the inherited component. For carbonates, because of this limit on knowing the initial, there is another formulation of this, what's called the Clara Wasserburg Concordia diagram. This was developed by Clara and Jerry Wasserburg at Caltech, a few decades ago. And the beauty with this system is you can plot your data, the same data, in this case, especially for young samples. The initial, in fact, you don't have to assume. You can calculate. You can calculate the initial by the projection of your Discordia chord. For most carbonate, the upper limit really intercept edges don't mean much. It's the lower intercept edges that are going to be relevant, but you can get the edge and the initial to 07 to 06 ratio. Absolutely wonderful. By the way, for those of you who are interested in kind of playing around with data and see how you calculate this stuff, there's a site called IsoplotR, maintained by the University College of London, and they have different remote sites. So if you just Google Isoplot R, you should be able to find the site. We use the regular Isoplot. A colleague of mine, Ken Ledwig, developed when he was at the Earth Geological Survey, and now is maintained at UC Berkeley Geochronology Lab. But but know though that before you get to put your data on Isoplot R or any other edge stuff, you have to do all the sort of corrections for spikes, for 234. But if you can get hold of some data, already corrected data, you can play around with it and see what kinds of things you can do. So this is a isochron edge for, again, AR03. The reason why this shows as linear, we're just looking at the very young age, basically, of the curve. The full curve kind of looks like this. So we're basically playing in this region in here. And as you can see, I'm also showing you the standard isochron for the 238 to 06 system in here for comparison. And you get, very good age of 3.28 million, plus or minus 100,000 years. With the standard isochron just the 206 to 38, you also get 328 versus 320, but the errors are a little more larger again. You can do even very young samples. This is an example for AR2, again, from WANA stuff. This is 740,000 years, plus or minus 0.11 to sigma. This is the 20, the reverse Concordia age. And then this is the standard isochron age of 238 to 06. You get similar age, 780 plus or minus 96,000 years. And then this is the letter also. Notice for very young samples, in fact, you are better off just getting a standard isochron age than the Concordia age. I mean, the good thing about this is as long as you get a meaningful concordant age, that you don't have to worry about any possible issues with the sample. But in terms of precision, the standard isochron actually might do better for very, very young samples. The 207 also gives a concordant edge, obviously with much larger errors, as I said previously. All right, this was short, but I wanted to leave as much time for question and answer. So, yes.
Sorry, thank you very much for such a nice talk and very creative demonstration. Now we'd be happy to take your questions, please.
Of course, there are not going to be any questions because I made it absolutely clear from the beginning to the end. So, no, I'm kidding.
We already have one actually. So from Dan, has possible fractionation of uranium, lead, uranium, lead, or thorium isotopes with changing rate of carbonate precipitation, temperature, and or redox conditions being investigated?
Well, so most of the work we do is in caves. So as a result, it's as ideal of a sort of environment as you can hope for. It doesn't mean you don't see altered samples, you do. But that doesn't seem, so caves by definition have, if they are large enough, reasonably constant temperature, they are fairly isolated. Even for things that have gone through submersion and back, some of our cave work, they seem to hold pretty well, but I can't just simply rule out. And the thing is, I like to quote Tolstoy's Anna Karenina, happy families are happy in similar ways, and unhappy ones are unhappy in countless ways. And for systems that are well-behaved, they tend to be very well-behaved, and you can see the stratigraphy is correct. You get concordant edges. And so I think by now I would say, typically we have a pretty good sense about systems that are behaving well and systems that are not behaving. In the uranium-lead case, you actually have, because you have this concordance issue between 238 to 06, 235 to 07, it's a double check. For uranium series, it may be a little bit of an issue, but not really. I mean, that's the beauty. We got started with the uranium series work on corals, and it became clear that the preservation is not going to be as good as speleothem. So that is not, I think the challenge in many cases is when you have detritus material, not so much the stuff that's coming in solution, but particulate matter gets deposits. And so the initial ratio corrections can be a little bit, can pose a challenge, whether it's uranium lead or uranium series. But overall though, and then also it can be in a very difficult environment, such as in the tropics, where in some cases, the uranium is leached because of the mobility of uranium, and therefore you don't have a lot of uranium to work with. But overall, though, I have to say, especially now that we've kind of cleaned up, I mean, not cleaned up, but kind of improved on our techniques, we do very well in most cases, believe it or not. In fact, we're feeling a little bold enough to go now to look at heterogenic type systems. I was kidding about making it all clear, so I encourage you.
Thank you very much. Hege also has a question. Hege, please go ahead.
Yes, thank you for this nice talk. I'm not so familiar with the uranium lead dating, so I was wondering, like the uncertainties, they're quite big, right? But the samples are also very old. Like, have you started working on a way to reduce the uncertainties, or is it just not possible with like, is it the best it can be, do you think, now with the method, or?
Yeah. Well, first of all, I don't want to impugn anyone in the lab or anyone working with us. If we were just shooting for the absolute, it is just kind of a matter of investment. So for an isochron, you probably need at least 5 points to make a decent isochron. Each of those samples has to be analyzed. So if you have literally, dozens and dozens and dozens of samples to deal with, it's how much time you want to invest getting there. It depends what issue you are trying to deal with. So let's say for our Pliocene work that we want to publish in Nature, we just needed to get the Pliocene within a certain bound. If we're really worried about, just reducing the errors, obviously, again, an isochron made up of, multiple samples. So what I showed you wasn't really our, with the idea of reducing iron. So there is a lot of ground to be improved. As I said, you can kind of see how much sample you can take out from a sample and how many years you can cover, right? So if this is, let's say, 100 years, and you are trying to get a precision of, let's say, a few thousand years, well, you can afford to take a sample like this, take the uncertainty of that, and then improve your counting statistics. So if we were trying to essentially see how ultimate precision would be, what I showed you is just, this was just routine work, people working on their PhDs, dealing with demanding advisors and getting ready for AGU or EGU. And so you kind of got to get things done. So yes, you can do a lot of improvement. Of course, then at some point you're going to run into limits, basically, for all the other limits you have to deal with in terms of initial ratio variability. You obviously have to reduce your blank up absolutely, and then the fractionation corrections have their own uncertainties. So I can tell you that you're ultimately going to reach to zero uncertainty. It's just what I showed you was someone coming into the lab in the midst of their busy work, trying to finish their PhD, doing their work, and getting the numbers. Of course, if you're doing with the more recent stuff like we've done with uranium series, you can get uncertainty in the age of plus or minus 5 years, no problem. But there, you're dealing with much shorter half-lives and very clean samples. Yes, there is more.
Thank you. I was just curious, but
No. As I said, by the way, we encourage anyone to reach out to us if you think you have projects that to put a little plug, unsolicited plug. And so if you have a project that requires defining timeframes in the range of 50,000 years, 2 million plus 50,000 years, I'm sure if it's reasonably well behaved, you can do it. It's just would require a little more effort.
Yeah, thank you.
Mm-hmm.
We have another question from Nella. Does recrystallization of carbonates affect the uranium lead method the same way as it affect uranium thorium in terms of possible disturbance of the system?
Yes, and more. From my point of view, lead is a very tricky element. The typical dust contains about 20 parts per million lead. So when I showed you that slide of our lab, this slide in here, the reason I showed you our air handler, I'm sure there were other more photogenic things I could have shown you, is there is a huge amount of effort involved in making sure that any procedural issue doesn't affect us. So lead is particularly sensitive. Uranium and thorium, yes, you can face issues with mobility, but lead, the contamination issue is something you have to be absolutely careful with. So when we do our lead, we have a special lab. Basically, we only do lead work or meteorites work only. And then as far as the systematics themselves, the uranium, obviously, if you have any recrystallization, this is going to go basically. And lead, as I said, is the issue is after crystallization, for example, if you get any fluid-drug interaction, the lead that is entrained in microparticles and other things can easily mess you up. So yeah, I making sure that if you have any sign of recrystallization or alteration, I would say it is not worth bothering with, unless that's the only sample from Mars and we have to work on it. My general feeling is, with most things, why bother with difficult things, difficult people, difficult anything, when you can deal with good systems, good people, fun. So just like samples, you want to. So we beat our heads like in the tropics. We did a lot of work in Central America, and we just were not getting. And then we got to this amazing place in Belize that has uraniums in the range of 4 parts per million. Well, that's a happy ground. You want to stay there and do work. Especially starting, try to work on projects that are tractable, that are problems that are clearly defined, sample sets that you can work with. Leave the difficult stuff to old people like me, just kind of, but for you young guys, work with stuff that is doable initially, and then you can work, unless you have a way of solving the problem.